Skylab, NASA's first attempt at having a laboratory in space, allowed innovative missions in space. One such mission included a series of life sciences tests. One of the tests was the lower body negative pressure test. It provided valuable information on the cardiovascular system. This was a measure of motor sensory performance, an experiment designed by a high school student. Using a punchboard apparatus, the crew's hand-eye coordination was measured on a daily basis. Balance, orientation, and perception, so important to man's ability to function efficiently in space, was another of the life sciences tests. The astronauts were instructed to exercise frequently, and one of the methods was the ergometer, or bike, to help them keep in shape. This also served as a test for changes in metabolic activity while working and living in a zero-gravity environment. Throughout each mission, a vast number of tests were made on the eyes, ears, nose and throat, and blood samples were taken and returned for post-flight testing. Skylab also gave astronauts the opportunity to test materials under zero-gravity and vacuum conditions. The formation of crystals was the most valuable of all the manufacturing experiments. It resulted in crystals 10 times larger than those grown on Earth, with a much better uniformity of composition, so important in the field of electronics. The aim was to develop electrical systems that would perform more functions, be faster, smaller, less expensive, and require less power. But it wasn't all work. The astronauts had a lot of fun. Even something simple like blowing bubbles was a whole new experience in space. They could puncture them, pull them, pick them up, but they still wouldn't break. As can be seen, getting from place to place was also no problem in Skylab. Weightlessness itself can be lots of fun, as Pete Conrad demonstrated. No circus performer or Olympic acrobat could match this. Although Alan Shepard was the first to play golf on the moon, this was the first spaceball game ever played. The tenants of Skylab returned to Earth after 28 days in space. It was a successful and novel mission in space.
Space Adventures, which had brokered deals to send US millionaire Dennis Tito and South African Mark Shuttleworth into orbit, plans to double its roster of successful space tourists by launching 2 people together in the next few years. Now, all they need is a pair of preposterously rich volunteers. Space Adventures said it would charge $20 million per 8 to 10 day round trip, similar to what Tito and Shuttleworth reportedly paid for their flights in 2001 and 2002. Despite the astronomical price tag, Space Adventures chief executive Eric Anderson said a dozen people from all over the world have already undergone medical tests for the flight and paid certain fees. So who will the lucky explorers be? Could there be a space wedding or a championship space chess match? Italian radio personality Roberto Ferrari has reportedly expressed interest. Pop star Lance Bass of NSYNC missed out on a chance to test zero gravity after an unsuccessful series of talks. Asked whether there is anything the hopefuls can do to prepare themselves for the mind-blowing experience of being in space, Dennis Tito replied that there was not, because it is so different than life on Earth. It's like life on another planet, almost like being a different species. Most of the ticket cost, enough to buy a Monet painting or a very fancy private jet, goes toward building the Russian Soyuz rocket flown on the trip, which is not reusable. The cash injection, which thickens Russia's space program budget, is a compelling reason to shuttle customers into space, said a space agency spokesperson. Space Adventures would not name any of the next potential civilian space explorers, but none of the people who had expressed interest had pulled out after the US Space Shuttle Columbia broke up in mid-air in February 2003. Space Adventures hopes to make up to 20 trips a year within the next decade or so.
During recent years, we have all enjoyed a flurry of stunning pictures of distant stars and galaxies. For scientists, such images provide new insights into the nature of celestial objects and thereby into the physics that determine their appearance and evolution. The sharper the images are, the better. This is why telescopes like the ESO Very Large Telescope and the Hubble Space Telescope are so important for scientists. Already long ago, however, astronomers realized that by using a special method called optical interferometry, they might be able to study their objects with much higher precision still. The only problem was that optical interferometry is exceedingly difficult to master. Interferometry requires the light from 2 or more telescopes to be combined. The Paranal Observatory in Chile, home of Europe's Very Large Telescope, the most advanced ground-based observing facility in the world, was conceived as an array of 8.2-metre telescopes. It was designed to work as an interferometer. But it meant doing interferometry on a scale never attempted before with any astronomical telescope. In March 2001, ESO carried out the first interferometric test observations with great success. Since then, the experts have worked on refining the technique while at the same time adding new specialized telescopes to the array. The new telescopes are 1.8-metre telescopes that, unlike their larger brothers, can move around on a system of rail tracks. This way, the distance between them can be varied according to the needs for individual observations. By observing the same object with different telescope configurations, it is possible to obtain images that are 100 times sharper than what can be observed with the Hubble Space Telescope. Only one of these special so-called auxiliary telescopes had been delivered to the Paranal Observatory up until a few years ago. Now, however, ESO has commissioned its second one. This means that interferometric observations can be carried out continuously without interrupting observations with the main telescopes. But the real importance of these additional telescopes lie elsewhere. The VLT interferometer will allow astronomers to study details on the surface of stars, or to probe protoplanetary disks and other objects for which ultra-high precision imaging is required. It is premature to speculate on what the Very Large Telescope interferometer will discover, but it is not difficult to imagine that there may be quite some surprises in store for all of us. It's 1963. Launching from Cape Canaveral, Faith 7 was the 4th American manned orbital flight. Its primary objective was to confirm how well man can function in space during a day and a half of weightlessness, and to test the efficiency of a human being as a primary component of a spaceflight system. Air Force Major and NASA astronaut Leroy Gordon Cooper Jr. named the flight Faith 7 for his faith and his friends. Cooper began flying at age 16 and was a jet pilot at 22. He also gained a degree in astronautical engineering and began the methodical and dangerous job as a test pilot. The demands of being an astronaut were now beyond even the demands of being a supersonic test pilot. New knowledge and training was required. As an astronaut, Cooper had to get used to weightlessness, a condition that at the time could only be maintained for very short periods. He underwent hours of training on centrifuges, experiencing the effects of steep acceleration, learning special breathing techniques to help him function during the crushing forces of liftoff and re-entry. He learned firsthand the sensations of being in a tumbling spacecraft and practiced the ability to control the craft under a variety of conditions. Astronaut Cooper flew dozens of missions, spent hours familiarizing himself with the components of his craft and mercilessly honing his skills. He learned operational procedures and emergency techniques. He became more acquainted with his Mercury spacecraft than he did his home. And he was trained to survive wherever the spacecraft came down. Special equipment was developed to monitor the astronaut's physical state at all times of the flight. Equipment measured temperature, both of the astronaut and his suit. Heartbeat and respiration rates were monitored with special gauges attached to the torso and under the arms of Cooper. Special microphones were attached to his arm on the brachial artery to monitor his blood pressure. The electrical output of the microphone and other gauges were fed into a single telemetry unit and changed into electrical signals. This was then transmitted via radio to doctors on Earth. Repeated use of this exerciser during the flight was also programmed to yield additional cardiovascular data on exertion while weightless. Relatively flexible use of his hands and arms are possible during normal flight since his suit is not normally pressurized. The atmosphere within his cabin is maintained at a life-supporting pressure. In an emergency in the cabin, his suit would be immediately repressurized to protect the astronaut. The suit is thoroughly checked just before launch. When Cooper left the preparation area to board the transfer van to take him to the launch gantry, he knew that his spacecraft had also been given a thorough examination in preparation for the flight. Many changes had been made from previous Mercury spacecraft to outfit Faith 7 for this mission. The 95-foot space vehicle consists of a reliable 3-engine Atlas booster and sustainer, the spacecraft, and the escape tower. Rescue crews were stationed at strategic points along his path in case of emergency landing before the completion of the scheduled 22 orbits of the Earth. The man, the spacecraft, and all the support teams must check out 100% before liftoff. Any problem causes a delay until rectified and given the all clear. There is no room for error when a man is launched into the void of space. Two brothers from the Montgolfier family made the very first manned flight in 1783. It consisted of a 5-mile flight above the streets of Paris. Another pair of brothers famously developed the forerunner of today's pressurized spacecraft in 1934. These famous brothers were Auguste and Jean Piccard. The brothers designed and invented a bathyscape, which contained a pressurized cabin and an artificial atmosphere for use in deep-sea research. It was the first such invention of its kind. The flights completed by the Piccard brothers led to the creation of complete environmental systems, which led to the ability to perform spaceflight. It is necessary for human survival in space to have a pressurized cabin. Spacesuits also need to be pressurized for EVAs and times when the cabin is not pressurized. The Piccard brothers also created such things as pyrotechnic devices to make possible explorations high above ground. These devices are explosive systems used for many purposes during spaceflight, such as separating launch stages, modules of spacecraft, and cutting the lines of parachutes after they had served their re-entry purpose. Here Professor Piccard is demonstrating the pyrotechnic device used for releasing ballasts from the balloon gondola. It works by placing a blasting cap in the center of the bag, which is then filled with sand. From within the gondola, an electric contact is made, exploding the blasting cap and puncturing the bag safely. That particular device was specifically credited with saving the lives of Professor Piccard and his wife, who accompanied him as an official photographer on flights. The pair were the only ones to successfully make a stratospheric flight in the 1930s, where they had to fly through clouds. Others died in these conditions. The balloon itself was inflated with 700 cylinders of hydrogen. Only a little gas is needed. This small amount of gas marks the difference between a stratosphere balloon and an ordinary balloon. In a stratosphere balloon, a small amount of gas is put into the top of the balloon until it's about 1/10 full. When the balloon is fully inflated, it's held by ropes until liftoff. 300 volunteers gathered to witness the event and to lend a hand. Out of all of them, only 6 had ever seen a balloon before. On the signal, all of the men moved forward a given amount so that the balloon rose evenly on all sides. The stress on the balloon became apparent at this stage. The lower part turns up inside and presented a remarkable sight. If they had taken off at this point, the stress on the balloon would have been too great and would have resulted in the material tearing in flight. The gondola is attached to the balloon by the load ring, and the load ring is held by 4 heavy ropes. At 6:58 p.m., there is takeoff from Dearborn, Michigan. Professor Piccard's wife is on top of the gondola, awaiting the signal from Ed Hill to cut the 4 ropes. As the ropes are cut with pyrotechnics, the gondola begins to arc back towards the ground. A command to get under the balloon and push us up comes from the gondola. The gondola is painted black on the bottom and white on the top to control the temperature. Inside the gondola, it is 67 degrees Fahrenheit, whereas outside, the temperature is at freezing point. The gondola itself is made of aluminium alloy, only 1/8 of an inch thick. The rate of ascent is 200 feet per minute, and when they get above the clouds, the ambient pressure is so low that their onboard supply of oxygen begins boiling off too rapidly. They quickly close the doors, which results in a hermetical seal for the gondola. Throughout the mission, the air is tested continuously for purity and was consistently in very good condition. After cruising over the top of clouds just below 10,000 feet, they finally land in some trees. These images are of man's journey into space. They are images of rare beauty as well as awe-inspiring accomplishment. Set to music, this vision supplied by NASA needs no words. One just has to gaze at the achievements that have been undertaken in the name of humankind. Skylab, NASA's first attempt at having a laboratory in space, allowed innovative missions in space. One such mission included a series of life sciences tests. One of the tests was the lower body negative pressure test. It provided valuable information on the cardiovascular system. This was a measure of motor sensory performance, an experiment designed by a high school student. Crystals was the most valuable of all the manufacturing experiments. It resulted in crystals 10 times larger than those grown on Earth, with a much better uniformity of composition, so important in the field of electronics. The aim was to develop electrical systems that would perform more functions, be faster, smaller, less expensive, and require less power. This also served as a test for changes in metabolic activity while working and living in a zero-gravity environment. Throughout each mission, a vast number of tests were made on the eyes, ears, nose and throat, and blood samples were taken and returned for post-flight testing. Skylab also gave astronauts the opportunity to test materials under zero-gravity and vacuum conditions. The formation of Skylab. Using a punchboard apparatus, the crew's hand-eye coordination was measured on a daily basis. Balance, orientation, and perception, so important to man's ability to function efficiently in space, was another of the life sciences tests. The astronauts were instructed to exercise frequently, and one of the methods was the ergometer, or bike, to help keep in shape.